Hello, new Algebra 1 students. I'm going to present with you a definition. The definition of absolute value is the distance from zero. The absolute value of a number is its distance from zero. And there's no such thing as negative distance. You can have a distance of zero. Zero is 0 units away from itself. It's just the point. Point has no dimensions whatsoever, no length. So the distance away from zero of zero itself is 0. But any other number has a positive distance away from 0. That's it. If you keep that definition in mind, you should succeed with anything you're asked to do with absolute value. Let me just go through 3 quick examples here. Of course, the 2 vertical line segments, that is not a parentheses. It has a different purpose than parentheses. The 2 vertical line segments are the symbol for absolute value. This statement here is asking you, what is the absolute value of 3? What is the distance of 3 from 0? And the answer, of course, is 3. But the distance away from 0 of -3 is also 3. -3 is also 3 units away from 0. So the absolute value of -3 is also 3. Now the absolute value of 0, as I said, is 0. The distance of 0 from itself is 0 units. And that's why, by the way, we have to have this or equal to sign here. It would technically be wrong to say the absolute value of any number is greater than 0 because the absolute value of 0 is 0 and 0 is not greater than itself. So this or equal to takes care of the situation where a is 0. If a is anything other than 0, it has a positive distance away from 0 because there is no negative distance. Now, this raises a new possibility for you. The possibility that when you solve an equation, you get more than one answer. And as you go forward in your math careers, you will encounter other situations, including in this course, including in this video, I will show you another situation where you get more than one answer to an equation. This is something you're going to have to get used to. But if you recall the definition of absolute value, you shouldn't have any problem. So here's an equation that you'll get, and they'll get more complex than this, but if you can master this one now, you'll be in a good situation. I'm going to switch to the letter X because there's a tradition in math that when we're showing general statements, like for example, the commutative property of addition, we say for all numbers A and B, A plus B is equal to B plus A. And the idea here is that the early letters of the alphabet, A, B, C, D, are used to mean just numbers in general, numbers that we're going to know what they are. And then the letters at the end of the alphabet, X, Y, Z, are typically reserved for unknown numbers that we have to solve for. That tradition is not followed all the time by all people in all textbooks, but it's one that I generally follow. And so I'm going to, rather than writing an A, I'm going to write an X. Now the letter is arbitrary. I'm just following a tradition here. The absolute value of X is, well, 3. Okay, here's an equation to solve. But I cannot give you credit for a correct answer if you simply say 3. Because there are 2 solutions to this equation. Think of it this way. You're being asked to identify all of the numbers that are 3 units away from 0. Well, there are just 2 of them, so I could have just said both rather than all. But X equals 3 or X equals -3. Here's something that's consistent. I've taught you many times that when you solve an equation, put your solution in for the X and see if you get a true statement. Well, if you put 3 in for X here, the absolute value of 3 is 3, true statement. If you put a -3 in here for X, The absolute value of -3 is also 3, true statement. So not only have I given the two solutions to this equation, but I've just proven or checked them as well. There is some notation in math that I'd like to introduce you to, and that is the set notation. There used to be a time in the teaching of math when I was very young, back in the 1960s, when there was a heavy emphasis on sets. And there'll be times in your math career when you might be more involved in talking about sets of numbers. Now, the word set is used in math in a similar way to how we use it in the everyday world. You could have a set of cutlery, a set of silverware that you use at your dining room table. You can have a set. A set is a very common word in the English language. It has many meanings, but generally means a collection of things. And in math, a set of numbers is simply a collection of numbers. Now, the symbol for set looks kind of like a parentheses, but it's got these little squiggly lines. It's squiggly lines indicating here comes a collection or set of numbers. And this set right here, in connection with this equation, we can call the solution set. It's the set of numbers that are solutions to this equation. And so in here we can put 3, -3. This set has two elements to it, two members to it, 3 and -3. It doesn't matter what order we put them in. We generally don't do that when we're solving equations that have one solution, like 2x plus 1 equals 5. We generally just say x equals the number. We don't put it in set form, but this sort of takes the place of writing the x equals 3 or x equals -3. You can do it a little bit more efficiently and realize this is the solution set to the equation. How about if we change this equation a little bit? How about if we write that? Now, if you follow the definition of absolute value that I started with, you should know what to say here. This is asking you the question, identify the numbers that are -3 units away from 0. There's no such thing as -3 units. Distance is always 0 or positive. So this equation has no solution. There's no number that's -3 units away from 0. No solution. You can write that. You can also write, to follow along with the set notation, you can say x equals the solution set. The solution set has no members. This is something that's done in math. You put the set brackets and then you don't put anything in there and it's empty. In fact, that's what it's called, the empty set. A set of numbers that contains no numbers is known as the empty set. There's also another symbol for it. This is one symbol. The other symbol for it is a circle. That's not a 0. It's a circle with a line through it like that. That's another symbol for the empty set, a set that contains no numbers. The solution to this equation, the solution set is empty. It has no elements. But if you find this strange, which you very well might, because I don't teach much about sets. Perhaps I should do that a little bit more. Maybe I'll talk more about various sets of numbers this school year. And when we get to certain topics in the course, sometimes those multiple solutions will be given in the solution set, like the previous one. But this has no solution. There is no number you can put where x is to get a true statement. So that's absolute value. The square root of 9. Technically, I think I made a mistake there. That what this really means what I just wrote on the board here, is the positive square root of 9, or sometimes called the principal with a PAL, meaning the main root of 9, which is positive. The thing is here, that when we write something like this, we agree. It's just an agreement among mathematicians. We're only talking about the positive number that you can multiply by itself to get 9. See, believe I've used the following kind of wording with you. I've said to you, this is asking you a question. What can you multiply by itself to get 9? Well, actually, that's not quite right. What positive number can you multiply by itself to get 9? That's what this means. This only refers to 3. And you may say, why is that? Well, it's by agreement. That's what mathematicians have agreed. Now, it is true that -3 times -3 is 9. And let me try to make this make a little bit more sense for you. Let's say we have an equation. X squared equals 9. Okay? This equation is telling us that you multiply a number by itself to get 9. Well, to solve this equation correctly, if you just write x equals 3 here, it's wrong. And I can't really give partial credit in a case like this, because it's extremely important to realize that this equation has 2 solutions. This is another situation in Algebra 1 where an equation will have more than one solution. We saw that with absolute value, and now we see it here. This exponent of 2 is an indication that there will be 2 solutions. Equations that have an exponent of 3, we won't talk about those very much this year, but they would have 3 solutions. And I'll talk more about that exponent dictating how many solutions there are. It's actually pretty important in math, so important that it's what I want to teach you eventually is called the fundamental theorem of algebra, having to do with the highest exponent indicating how many solutions there are to the equation. We will talk about that more. There's a little bit more that I need to say about that later. But for now, I think you can agree with me that 3 times 3 is 9, and -3 times -3 is also 9. But back up here, I told you that when we write this symbol, the square root of 9, we're only referring to positive 3. So how do we solve this equation? Here it is, very simple. If you have an equation in this form, x squared equals a number, here's the solution. X equals plus or minus the square root of 9. Now this is some symbolism here. Mathematicians, you could make a case, mathematicians are lazy. That would be sort of a negative way to phrase it. A better way, a more positive way to phrase it would be, mathematicians like to be efficient in how they write things. The symbolism of math is efficient. And a good example is AB. You write AB, or you write 4A, and it means multiplication, right? A times B or 4 times A. Why? Because mathematicians agreed to that, and you don't have to write an X between, 4XA or AXB. If we agree that AB means A times B, it's sufficient, okay? So this, let me write out what this means. This means X equals the positive square root of 9, or X equals the negative square root of 9. You see how much more writing that is? I had to write the X twice. I had to write 2 equal signs. It's simpler to just write it this way. X equals plus or minus the square root of 9. You have to realize that that's referring to 2 numbers. This is saying this more efficiently. Now, the square root of 9 happens to be 3. So we can further simplify like that and say that X equals plus or minus 3. x is positive 3, or x could also be negative 3. Two solutions. I suppose going back to our set notation, we could say that x equals this set of numbers, 3 or negative 3. You do it that way as well. This is probably going to be the preferred way that we'll write the two solutions to that equation. And the next thing I'm going to do is something that every year causes problems for students. And some of you might have faced it already in 7th grade. What if that 9 is not a perfect square? Well, the frustration and difficulty that students face with a situation like that is really unnecessary. Let me pause and then I'll show you what I mean. The reason students have trouble with x squared equals 10 is because they haven't followed my advice about approaching it reflexively. I would like you, when you encounter an equation like this, x squared equals a number, to have an automatic mental reflex. We've all had that experience with our physicians. The physician taps our knee with a little rubber hammer and our knee kicks out involuntarily. A reflex. Well, brain is not like the muscle of your knee, but we can make the analogy. You see x squared equals 10 and you immediately write this as a reflex. X equals plus or minus the square root of 10. Those are the two solutions to that equation. It's just like x squared equals 9. We approach it the same way, except the square root of 10 is not a whole number, and neither is the negative square root of 10. Not only is the square root of 10 not a whole number, it's not a fraction either. It's irrational. That's what gives students trouble, because they think that they have to come up with an approximation for the square root of 10. They may even mistakenly think there's a fraction, like they may think it's 3.5 or 3 1/3 or something like that, or negative 3.5, negative 3 1/3. But it isn't. The square root of 10 is irrational, meaning it cannot be represented as a fraction. On the calculator will tell you that the square root of 10 is 3 point, and then it'll give you a whole bunch of digits as an approximation. Those decimal digits go on forever without any repeating. You can never put a bar over any of those digits like you can with some fractions. So your worries are needless when you have x squared equals 10. These two solutions here are exact solutions. Let's see why. As we've said many times, you solve an equation, you put your solution, or each one, in this case there are two, in for x in the original equation, and you get a true statement and you know that it's correct. Well, let's put the square root of 10, the positive one, in for x here. Now, when I write the two solutions, plus or minus the square root of 10, I've got to put the plus sign here to just, if I left it out, I'd be saying that the only solution is the negative square root of 10. But if I just write the square root of 10 like this, as I said earlier, that's the positive. We agree that this is the positive square root of 10. All right? So now I'll square it, because the equation is x squared. All right? And this, of course, means the square root of 10 times the square root of 10. And what is that? Well, don't worry about the decimal approximation of the square root of 10. The square root of 10 times the square root of 10 is 10. Why? By definition. That's what the square root of 10 is. The square root of 10 is the number which, when you multiply it by itself, which is exactly what we're doing here, you get 10. Let me say that again. The square root of 10 is the number which, when you multiply it by itself, you get 10. So that's why it's the solution to x. When you square the square root of 10, you get 10, because that's what the square root of 10 does. That's what it is. Okay. Now there's another solution. The other solution is the negative square root of 10. So now I'll put the minus sign in front of it. When I put the minus sign in front of the square root of 10 symbol, now I'm referring to the negative square root of 10, which of course is the same number except on the other side of 0. The square root of 10 is a little bit more than 3. The negative square root of 10 is a little bit less than negative 3, right? So what does this mean? Well, it means the negative square root of 10 times the negative square root of 10. Negative times negative is positive, and the square root of 10 times square root of 10 is 10. So this is also 10. See, the negative square root of 10 is a solution to this, one of the two solutions, in the same way that negative 3 was a solution to x squared equals 9. Same thing. The only difference is that the square root of 9 is 3. The negative square root of 9 is negative 3. With the square root of 10 and the negative square root of 10, neither one of those is 3. Neither one of those is a rational number, but they still serve beautifully as the two solutions to this equation. So there you go. What about this? X squared equals negative 10. This equation is asking you a question. It's asking you, what number can I multiply by itself to get negative 10? What number can I square to get negative 10? And the answer is, there isn't a real number that you can square to get negative 10. Just think about the real numbers. What kinds of real numbers are there? Well, there's 0. 0 is a real number. But 0 squared is not negative 10. How about a positive number? Is there any positive number you can multiply by itself to get negative 10? No. Positive times positive is positive. What about a negative number? Is there any negative number you can multiply by itself to get negative 10? No, because any negative times negative is positive. Okay? This equation has no real solution. That's what we have to say. It's technically incorrect to say that there's no solution. In your minds, you can kind of think of it as being no solution because you have no introduction yet to the fact that there are numbers that are not real. Now remember, what are the real numbers? They are points on a line, points on the real number line. Well, to a small degree in Algebra 1, later on in the school year, and a little bit more in high school math, you need to come to terms with the fact that there are numbers that are not real. They don't exist on the real number line, but they exist in some way in mathematics, and I'll touch on this a little bit later. Please don't be intimidated by it. I know it sounds weird to say that there are no real, so if they're not real, what are they? Imaginary? Well, we actually sometimes use that word imaginary, but it's not imaginary like, purple unicorn, okay? The imaginary numbers that I'll introduce you to a little bit in math, they're numbers. They're necessary numbers in certain situations. The word real is sort of a term of art. It's not really being used in its everyday sense. It's simply referring to the numbers that are on the number line that we all are familiar with. There's no point on that number line, that real number line, that will solve this equation, because the real number line only has positive reals, negative reals, and 0. That exhausts all of the real numbers. And I just went through how none of those works. Positive numbers don't work, 0 doesn't work, negative numbers don't work in this equation. So there's no real solution. When I was introducing absolute value, I was able to say, for all numbers A, the absolute value of A is greater than or equal to 0. But for this statement here, for all numbers A squared is greater than or equal to 0, I technically have to insert that word real. because there are some numbers that mathematicians were sort of forced to come up with, forced to recognize. Numbers that when you square them, you get a negative number. Okay? They're not real. Okay? Don't worry about, it's not as weird as it sounds, but I just want to make you aware that there are numbers that are not real. Let's restrict ourselves to real numbers here. So for all real numbers a squared is greater than or equal to 0. Okay? Now, I just went through that when in talking about why x squared equals negative 10 had no solution. Any number that you multiply by itself is either going to be positive or 0. If you square 0, you get 0. So we need that or equal to symbol right here to account for 0. But any other number that you multiply by itself will be positive. Any other real number. Okay? So there's that. I'd like to actually jump back to absolute value now. I'd like to present you with one absolute value equation and two absolute value inequalities. After we learn to deal with absolute value in equations, we go on to a bit more challenging topic of absolute value within inequalities. Inequalities are statements that have symbols like less than or equal to, greater than or equal to, not equal to is also inequality, a symbol other than the equal sign. And for the inequalities, it's going to be very useful for us to use the number line to show our solution. Okay? Now, you can follow what I'm going to discuss here with just an understanding of the definition, just a knowledge of the definition, that the absolute value of a number is its distance from 0. So let me go back to an equation that's very similar to one that I already used. I think I used the absolute value of x is 3, so let's not repeat that one. Well, how about the absolute value of x equals 4? It has two solutions. There are two numbers that are 4 units away from 0. And I showed you before that we can say that x is the solution set containing -4 and 4, or we could say x equals -4 or x equals 4. Either one of those is correct, all right? But let's do something else, and this is really preparing us for the inequalities that I'm going to show you. Let's graph the two solutions. Well, that's very simple, right? To graph the two solutions, there's 0, let's call that 4, and the same distance to the left of 0 would be -4. So here's a real number line. How can we indicate these two solutions? Well, we can put a point at -4 and a point at 4. These two solutions, these two ways of writing the solution, we can call algebraic. And this solution, this way of representing the two solutions, is geometric. A line is geometry. It also is referred to as the graph of the solution. Again, graph is visual. Geometry is visual. You look at something, okay? And that something being the number line. Okay, now I'll say this. In math, we don't often graph solutions when they're a single point, or in this case, 2 points. We didn't do that when you first learned to solve equations. Remember, when you first learned to solve, say, 3x plus 1 equals 13. Well, you get x equals 4 there, right? That's easy. X equals 4. We didn't generally go to a number line, find 4, and put a point there, but we could have. This would be the algebraic solution to the equation, and this here is the geometric or graphing, the graph solution to the same equation. These two things say the same thing. X equals 4, algebra. number line with a point at 4 also says x equals 4. Okay. We don't do this generally because it's so obvious. When you say x equals 4, it's obvious you mean that point and no other point. But when we are dealing with inequalities, the graph solution is helpful for us to understand everything that's involved in the solution. So let's now look at two inequalities involving absolute value. So here they are. The absolute value of x is less than 4, and the absolute value of x is greater than 4. These are inequalities. They have symbols of inequality in them. Now, I want you to understand, I'm kind of jumping ahead a little bit here. My message today, part of my message today has been absolute value, which is why I'm getting into this, to continue to explore absolute value. The reason I'm sort of skipping ahead here is that before we get to these in the chapter that they're in, it's chapter 2 or 3, before we get to absolute value inequalities, we will review inequalities that don't have absolute value in them, like 3x is less than 12, or negative 3x is less than 12. And inequalities that are a little bit more complicated than that. These will come before the absolute value inequalities. But you can understand the solutions to this today just with the definition of absolute value. This is asking you, what is this asking you? Where are the numbers that are less than 4 units away from 0? The absolute value of a number is its distance from 0. This says the absolute value of x is less than 4, so x has to be less than 4 units away from 0. Where are those? If I asked you to indicate, I'm going to do the graph answer first. I said a moment ago, we graph solutions to these inequalities because it helps us to understand. I think it's the first place maybe that we go to. It's easier to do the graph solution to these inequalities than it is the algebraic. I'll show you the algebraic, but here's the number line. 0, 4, negative 4. Where on that number line are the numbers that are less than 4 units away from 0? That's what this says. Aren't they here? I'm going to use red. Aren't they near 0? You know, we have to restrict that number line to just the portion of it that's close to 0, within less than 4 units away from 0. These are all the numbers indicated in red that are less than 4 units from 0. Nothing over here is less. This is not less than 4 units from 0. 5, 6, 7. Neither is negative 5, negative 6. They're not less than 4 units from 0. They're more than 4 units from 0. Now, in textbooks, often this would have been a darkened line segment right on top of the real number line. But when you're writing it out by hand, I think it's clearer to just sort of go above the line. But it's in the books, it would be a thickened line segment between negative 4 and 4. Notice I put open circles at negative 4 and 4 because 4 is not less than 4 units from 0. 4 and negative 4 are both exactly 4 units from 0, not less than. If this had been or equal to right there, I would have filled in those circles, right? Filled in the circles because then it would be the numbers that are less than or equal to 4 units from 0. So there's the first one. Okay. Let's go on to the second one, and then we'll come back and talk about how to represent these solutions algebraically. The other one asks a completely different question. Where are the numbers that are more than 4 units away from 0? So We'll set up the number line the same way. The only numbers we need to indicate on this number line are the 4 and the negative 4. And we'll put 0, of course, right in the middle between the 4 and the negative 4, right? So just think about it. Where are the numbers? Where are all of the numbers that are more than 4 units away from 0? Well, anything to the right of 4, anything to the right of 4 is more than 4 units away from 0, and anything to the left of negative 4 is more than 4 units away from 0. Right? It's a completely different looking graph. This graph here, it's a line segment that's 8 units long. Right? And I think whether this circle is colored in or not, it's still 8 units long. I'm pretty sure of that because points have no size. But you cannot ask how long. There's no line segment there. You can't ask how long is the answer. This answer is 8 units long, but this one here, that goes infinitely to the right. This goes infinitely to the left. So the length of the solution is infinite. You can't really talk about it. Okay. If you keep in mind that absolute value means distance from 0, these solutions should make sense to you. Now, and they truly are solutions. This graph is the solution to this inequality. This graph is the solution to that inequality. You are going to be responsible for representing the solutions algebraically, however. And this gets into a tricky little matter of the difference between the word and or. Maybe we don't think about that in our everyday lives. We use those words over and over again in the course of our lives without thinking, and usually we don't have to think about them, but here you do. In order to indicate algebraically this solution here to the absolute value of x being less than 4, you have to say this. You have to say that the x is less than 4, the numbers that will work. Okay, you're trying to identify the numbers that will work. Well, they have to be less than 4. Nothing greater than 4 will work, right? And 4 doesn't work either. But that's not enough to say that the x has to be less than 4, because the x also has to be greater than negative 4. Okay? If you just said x is less than 4, that would include negative 5, negative 10, negative a million. But those are not part of the solution. They're not less than 4 units away from 0. So you have to do this. You have to say, and x is greater than negative 4. Both of those conditions have to be met. And just try to convince yourself that that's true. Both of those conditions have to be met in order to be within 4 units of 0. You have to be less than 4, and at the same time, you have to be greater than negative 4. It's the word and there. Well, over here, all right? This graph solution, which is correct, it's a correct solution to the inequality. Well, this part over here says x is greater than 4, right? Any number that's greater than 4 will be a solution. Or, and these are terms of art here. Here you have to use the word or. Or the x can be less than negative 4. Okay? It's a little bit tricky because of the way we use these words in the ordinary English language. For example, I'm going to do something now that is really wrong. It may not sound wrong, but it's wrong. Let's look over here. The absolute value of x is greater than 4. Well, that includes the numbers that are greater than 4 and it includes the numbers that are less than -4. See, I use the word and there. There are two parts to it, this part and that part. But you gotta convince yourself that what you really need there is or, because let's look at it this way. X is greater than 4 and X is less than -4. Now, this statement here, let me put a big red X through it. Okay? That was the word and. I'm not trying to confuse things, but if you were to say X is greater than 4 and X is less than -4, are there any such numbers? Are there any numbers that are both greater than 4 and at the same time less than -4? The answer is no. That's why we have to use the word or. Even though in our everyday speech we might say, well, the solution to this includes the numbers that are greater than 4 and it includes the numbers that are less than -4. Now, saying it that way, I guess, is not wrong, but we have to, if you put those two together, you know, X is greater than 4 and X is less than -4, there are no numbers that satisfy both of those conditions. It's really an or. So you'll get used to this. Some students like to think that when you have a greater than sign or a greater than or equal to, the word or will be in the solution. You can, you know, sort of memorize it that way. And when you have a less than or equal to, the word and will be in the solution. Just try to come to terms with this a little bit. And if this confusion between the word and the word or is still there for you, at least understand the graphs. If you can understand the graph solutions, that's progress. That shows understanding. So I'm gonna stop it there. Strangely enough, we're a little more than 42 minutes, which is about a little less than a typical class period. So I may be releasing this in the summer, but it's not part of your summer assignments. By the way, those 3 assignments that I gave to you spaced out during the summer, if you haven't done those, please get them done by August 25th, so that when you come to school on the 26th, they will be done. I would appreciate hard copies of them. Bring them with you to school the first day of school. Even if you submitted them electronically, please hang on to the hard copies so I can collect those. And this one here, this video, if you don't watch it during the summer, watch it during the first week of school. I would like it to be sort of part of your first week of school homework. So enjoy, and let me know if you have any questions. I love to answer questions about math. Bye-bye for now.